Alright gang, here we go. Quantum mechanics. So this is gonna blow your minds. Okay, so last time we talked about the Bohr model, and we talked about how the electrons, or Bohr came up with the model where the electrons orbit the nucleus, right, in circular patterns. We kind of talked about what that might look like. Now this model works really, really well for hydrogen atoms only. Okay. But then after that, it doesn't work. Okay. Okay, so it's a giant failure everywhere else, but that's okay. So there were three main scientists that kind of helped us come up with the quantum theory. Okay, the first guy, I'm sure you've heard of him, was Albert Einstein. Yeah, probably heard about him. Yeah. So he came up with this idea that light itself behaves both as a particle and a wave. So a particle meaning just like an individual point of something. So it acts like that, like you can like hit it. It can go in straight lines. It's in a specific place at any given moment. Okay, but then it also have wave properties, which is what we've been talking about so far. So it also travels through space kind of like a wave. It has energy defined like a wave. It has an amplitude and a wavelength and a frequency. Okay, so he kind of pioneered this idea, and based on that is really where we came up with that idea E equals mc squared. All right. Now each photon, he also described as each photon, and remember a photon is like a particle of energy or light, is described as having a quanta. So remember we talked about quantization in the previous video. So it means a specific amount. Alright? So each photon that's traveling around has a very specific amount of energy, and it can deliver that energy to something else by hitting it, or it can release energy and the electrons can release energy when it comes down from an excited state back to its ground state, right? Alright, then the next scientist, so that was Einstein. The second scientist is this guy named de Broglie. Okay, um, and he kind of built on this idea that Einstein said that light behaves as a particle and a wave, and he said that all particles of any matter can behave as waves too. So that means like if you threw a baseball, that baseball would make a parabolic arc and kind of come down and hit somewhere, right? You throw it, it falls, hits the ground somewhere. Well, at the same time it's doing that, it's also acting like a wave, okay? And completely changed the way we approach the idea of microscopic and atomic-sized particles. The thing is, when we talk about macroscopic things, or about the size of the things that we can see and touch, their wave properties are so minuscule that it doesn't really affect anything about them. So our basic physics and stuff that Newton came up with isn't changed at all. But as we start to get to really, really, really small masses, the wave properties start to take more and more importance. So especially with electrons, this is the mass of an electron, 9.11 times 10 to the minus 28th grams. That's ridiculously small. So its wave properties start to become much more important. Okay, you don't have to have this memorized, this mass of the electron, but you should know that they're like stupid small. They're so much smaller than a proton and a neutron that we just essentially say that they have zero mass. Okay. So anyway, so when we talk about quantum mechanics, even though all matter has some wave and particle properties, even us, we really don't care about the wave properties until we're talking about subatomic particles. Okay. So remember, these are the electrons, protons, and neutrons that we talked about in the previous unit. The final guy that helped us kind of establish electronic behavior, or the behavior of electrons, is Schrodinger. Okay, and Schrodinger, you might have heard of Schrodinger with his cat experiment. So this was a thought experiment he came up with, and kind of just trying to explain the idea that of the Heisenberg uncertainty principle. Okay, so he took a cat And you guys all witnessed my superb drawing abilities. So we've got a cat, yeah? Put him in a box. So we close the box. Inside the box, we put a container of poison. Okay? So here's our poison symbol, skull and crossbone. Yeah. So inside there we have our container of poison, and that poison is attached to a random alpha particle generator. Okay? So we've got an alpha particle generator, and when we don't know when that generator is going to shoot an alpha particle, but when it does, it'll hit the poison gas container, open up the poison gas, and our cat will die. Okay? He didn't actually do this. This was just a thought experiment. Okay? So he said, like, okay, we're going to put this this container of poison with this alpha particle generator, and this cat will close the lid, and because we don't know when the poison will get released, by our view, the cat is both alive and dead. Oops, I should say alive and dead. Okay? At the same time, because we can't decide, based on the information we have, we don't know when the poison is going to get released. And so right now the cat could be alive because the poison hasn't gotten released, or it could be dead because the poison did get released. Okay, so it's like this idea of both things exist at the same time. Okay, so when we're talking about electrons, Heisenberg came up with this idea that we can't know both the momentum and the position of a particle at the same time. We can't know if the cat's alive or dead at the same time, so we can't know whether or not the electron is in a specific place and where it's headed next. Okay, so instead of deciding that electrons were orbiting at the nucleus, really the idea is that the electrons could be anywhere. Okay, but there's a higher likelihood of finding those electrons in certain spaces. Okay, so we call it a probability density. Okay, so we use what's called an electron cloud, okay, to describe the highest probability. Okay, so electron clouds describe the highest probability, and we're trying to finding that specific electron within a certain volume. Okay, so right here we've got our x-axis that comes in and out of the screen. Our y-axis goes left, right, and our z-axis goes up and down. These blue dots represent the most probability places of where the electron could be. Notice how towards the middle, where our nucleus would be, where it's much more likely to find that electron. But there's still, possibilities of finding that electron all the way around it. All right. So that's kind of the idea of the electron clouds. And so as we talk about orbitals, we're not, in the next couple of slides, remember that orbitals doesn't mean it's orbiting that path. It means that these are the places it's most likely to be. Alright, so first we need to just refresh ourselves on energy levels. So remember our Bohr model, we talked about energy levels. We had n equals 1, 2, 3, etc. Right? Okay, we talked about how as these go up, we get higher energy. Okay. They also mean we're farther and farther from the nucleus. So n equals 1 is the first energy level, and we're closest to the nucleus. Okay? And then we can just keep going up from there. As we go up energy levels, we are getting farther away, and also energy is increasing. Okay? So as we go down, energy is going up. Okay? Now, each energy level can hold 2n squared electrons, where n is equal to the energy level. Okay, so when we're at the first energy level, when n equals 1, our number of electrons equals 2 times 1 squared. Well, 1 squared is just 1, so that equals 2. So n equals 1 can hold 2 electrons. At n equals 2, we can have 2 times 2 squared electrons. So 2 squared is 4 times 2, so we get 8 electrons. Okay. At n equals 3, it keeps going. Alright, so why don't you pause it and try to do n equals 3 and n equals 4 on your own. Alright, hopefully you got that. So you got 2 times 3 squared. So 3 squared is 9, so we get 18 electrons. And then n equals 4. We got 2, 4. squared, so 32 electrons, right? Because 4 squared is 32. So notice how as we get higher and higher energy, we can have progressively more and more electrons fitting in. Okay, so it's this exponential growth of number of electrons that can fit in each energy level. Alright, so that's our energy levels. Within each energy level, we can have what are called sublevels. Okay, so, and those sublevels describe the shape. Okay, and remember, these shapes are the density shapes. Okay, so down here you can kind of see I pulled up some more pictures about probability densities. Okay, and so these are literally just mathematical relationships of what these electron spacings might look like. Okay, so S is spherical. Okay, so when we talk about S orbitals, we're really just talking about spherical shapes. Okay, when we talk about p orbitals, they're these dumbbell shapes. Okay, so these are S, and the probability densities look something like this. P orbitals will look something like this. Okay, and d orbitals make this cloverleaf shape. At least 4 of them do. The 5th one is all funky looking, and I'll show you a picture of that in a minute. So anyway, so D makes this cloverleaf shape, and then F makes a ridiculously complicated a whole slew, 7 different complicated shapes. And I've got some pictures to show you of those too. And I've also got models that I'll probably pull out, here in a day or two. That's going to kind of let you see them more 3D, what these sublevels look like. So remember, you do need to know what these shapes are. So you need to be able to memorize these, okay? Alright, so you should know that S's are sphericals, P's are dumbbells, and D's are cloverleafs, and F's are complicated, okay? Yep. So orbitals are the possible 3D orientations of each sublevel. So these are, once again, it's just the shape. Okay, S sublevels have 1 orbital. Now each orbital can have 2 electrons. Okay, so this means every single S sublevel has 2 electron slots, 2 places where electrons can be. Every single P sublevel has 3 orbitals, and each of those orbitals can have 2 electrons. So that means we have 6 electron places for those. D sublevels have 5 orbitals, so that means there's 10 electron slots. And F sublevels can have 7, so that means they have 14 electrons. Alright, so the checkpoint for this will make a lot more sense. Like, you'll kind of have a better idea of how this all kind of works into the periodic table once you start working on the checkpoint. And this is an interesting checkpoint. We'll actually do it pretty much together, filling out that periodic table that's at the very back of your note packet. Alright, so here's the shapes for S orbitals. Like I said, S orbitals are always spherical. We can have 2 electrons in here, right? Okay. Now, P orbitals, look how, so the main thing I want you to get from these is their orientation. Okay? I don't know why this one was included. Forget this guy right now. Alright. So look at their orientation. So we have one dumbbell that's oriented on the x-axis, another one that's oriented on the y-axis, and then another one that's oriented on the z-axis. Okay? So remember, we can have 6 electrons. 1, 2, 3, 4, 5, 6. 1 electron can fit on each side of this dumbbell. Okay, so these are like the likelihood when all of these p orbitals are filled. This is like the likelihood of finding an electron would be most likely within these shapes around the p orbital. Okay, and the d orbital, these are your cloverleaf. Notice how they're named based on both planes they're on. So this guy is oriented on the y-axis and the z-axis, and the x and the z, and then the x and the y. And then these last 2 are real funky, okay? Because now we've got 2 more orbitals. Remember, d orbitals can have 10 electrons total. Anyway, so these are the different shapes your d orbitals can make. And finally, your f orbitals, look at these suckers. My personal favorite is this guy over here. So you don't need to know what these shapes are, but I threw these in there just so you could have a kind of an idea of what these things look like. So, and really the idea is that these are all predicted mathematically. Okay, so we came up with what are called wave equations that kind of give us an idea of where these electrons exist. Okay, and then we can use what's called a scanning tunneling microscope. Okay, very expensive, complicated piece of equipment that lets us actually look at electron clouds. Okay, so here's our 2s orbital. Our 2s electrons can either fit in here or in here. Okay, and then our 3p's, so they're like this, right? These are our dumbbell shapes. Yeah, and they can be arranged like this. Oops, like that. And then our D's, here are your clover leaves, and then look at your F's. Look at that guy, so cool. Last quantum number that you need to know about is called the spin quantum number. Okay, so you'll see them written as m sub s. Okay. Now, pretty much all you need to know about this is that when we have electrons that are in the same sublevel, the way we tell them apart is that they're going to spin in one of two directions. One electron is going to spin clockwise, and the other electron is going to spin counterclockwise. We also sometimes call it up and down. Okay, so one is spinning up, one is spinning down. And that literally means, remember how they're actually a particle, they're both particle in the wave. That means the actual particle is actually spinning one way versus the other. Okay, and so when we notate this, we'll really just call it ups and down. Spin up, spin down. And that's it for what you need to know about quantum numbers, or about quantum models. Alright, so as soon as you feel like you have a grasp on this, you go ahead and pull or go to the back page of your note packet, and you'll find like what looks like a coloring page of a periodic table. And we're going to go ahead and work through that and color that together in the next video. I think it's called like quantum number checkpoint or periodic table checkpoint or something like that.